Today I'll be explaining Starlink by SpaceX, presented by me and cited from Branch Education. So what is Starlink? So Starlink is essentially a satellite internet constellation which is operated by SpaceX, which aims to provide fast and stable internet to anyone from anywhere in the world. It works using 10,000 plus satellites and an individual satellite dish for each connection. So my explanation here, for my explanation, I'll be distilling information and using visuals from the 28-minute detailed video by Branch Education of the oversimplified workings of Starlink. So this is a satellite dish which is placed on your house and sends and receives signals very fast to a moving satellite that is very far, which is continuously angling or steering the beam of data to the satellite, and the disk, which is from which satellite it transmits to every 4 minutes. So it keeps on switching the satellite. It's not one constant satellite. So this is a TV satellite dish, and it focuses the electromagnetic waves that are sent from the TV satellites into this one area, and that's how it processes it. Which as you can see, are much farther than Starlink satellites. The TV satellites are very far. The TV satellite dish can only be used to receive data. It cannot transmit data to the satellite. However, the Starlink dishy, which is fondly, as Elon Musk fondly calls it, can receive and send data and transmit data. Although the Starlink satellites are 60 times closer than TV satellites, it's still a hard task to transmit the data wirelessly and across the distance. So in order to do that, to achieve this task, the satellite dish needs to focus tight, powerful beams that are continuously angled to the moving satellite. When compared to TV satellites, the TV satellites are larger and they spread the rays to a wider, signals are wider. Starlink satellites need to be in low Earth orbit in order to provide smooth latency and to provide internet as a result, the coverage is much lower. So it's smoother internet, but the coverage is lower. Therefore, 10,000 plus satellites orbiting the Earth at incredibly high speeds in the low Earth orbit are required. So let us see what's inside Dishi. The insides of Dishi contain two motors which are only used in the initial setup to get the dish pointing in a general proper direction. It is not used to angle the data to the satellite. This is the PCB or the printed circuit board. It contains 20 large microchips and 640 small microchips, the main CPU and the GPS module. The other side of the PCB contains copper. So overall, the satellite contains 1,280 antennas arranged in hexagonal pattern. This is a single antenna, which is controlled by a microchip here and has 6 layers. So the electricity flows from the microchip through the feed line to the patch. The charge is positive when it is at the peak of the wave here. And the charge changes every 83 picoseconds, which is the 12 billionth of a second, and becomes negative at the throw of the wave here. When it is at the throw, the flow of electrons repel all the electrons to one side. So it's negative, it repels all the negative to one side. Therefore, making one side negatively charged and the other positively charged, thereby creating an electric circuit and with the wire and the patch. Therefore, when the wave reaches its peak, as you see last, it was at its stroke. When it reaches its peak, the flow becomes positive and the charges flip or oscillate. And as the wave changes from its peak control, and the direction of the electric field also changes. As you can see, due to the oscillation of the electric field, a magnetic field forms perpendicular to the electric field and flips also as long as the current flips. It's perpendicular. Because of the magnetic field being generated perpendicular to the electric field generated, the wave moves from in a curved like balloon-like fashion. So this is how the field is formed in both the cases. This method can be used to receive instead of transmit by switch. In this, the microchip provides electricity. In that, its electricity is taken, or the charge is taken from the signals, and then it's amplified here and it's given back. The dimensions are also made so that it receives only a certain radio waves and ignores others. That's how it's like particularly cut. All the displays are very oversimplified working of this antenna, as these are only like less than 2 parts of the 6 layers. So it's a very complicated process. A single antenna does not have enough power, as its signal would be like turning a light bulb and trying to see it from the International Space Station. So what we need to do is make this signal 1,000 times brighter and focus all of these waves into a single powerful beam. In order to achieve this, we use 1280 of these antennas in a PCB on the copper side in a hexagonal array using a technique called beamforming. So we're going to explain beamforming now. So this is the signal when one antenna transmits. You can see the peaks and the throws and everything. This is the bubble-like, I mean the balloon-like area. So this is when two antennas transmit. As you can see, they can overlap. In some areas, the electric fields or the antennas are pointing in the same direction at overlapping peaks and thus add together via constructive interference. In other areas, opposite happens with one peak on a throw and they cancel each other out with destructive interference. So the area formed is of constructive interference, which is far tighter in focus with one antenna alone. See the two, they're focused and they're much stronger. When we add even more antennas to the zone becomes even more focused and is called beam front or wave front. Now with 1280 antennas, we can use the beam to reach outer space. This is the scale. In fact, the power is not increased by 1280, but 3500. The reason, though, is very complicated and simply means the waves get mirrored, passing through and pass through a small space. Our next step is steering the beam towards the satellite. Beam steering is done by a process called phase shifting and changing the amplitude and frequency. So the amplitude derives the power of the signal frequency, as you can see. More amplitude, more power, less amplitude, less power. And the frequency determines what the signal is or the hertz of the signal, as you can see. It's a different way. Phase shifting, phase shifting is the signal of the wave, shifting the signal of the wave. So the degree of the signal moves back or forward is similar to a circle. So for example, this is moving 45 degrees forward. So the signal is moved like that. And you can compare it to angle in a circle. So it's moved 180, it's moved like that. So obviously, phase shifting, our eyes really can't identify the degrees of phase shifting, but PCB is really good at it. For example, this is 315. We wouldn't know if it's just like 315 or just 15 because we can't differentiate, but the PCB is really good at differentiating. So we use phase shifting to angle the constructive interference. So if it's like 45 degrees, it's at this side because we are making the waves overlap at a different point. So you can control what direction they are. So at minus 45 degrees, there's that point. And destructive interference cancel out. So it's like only this direction. So this is only showing with the bubble-like, balloon-like wave. So using this, we can control the angle where the wavefront is formed, so we can steer the beam in a direction or another. So this is where it will be transmitted. This will all go to space, and this will go to the satellite. So the GPS chips tell the coordinates of the satellite dish to the satellite, and another chip in the PCB gives the angle of each of the 20 big chips, which each sends to the 32 smaller chips, which each send to two antennas. This happens every 2 microseconds to be accurate and have proper communication with the satellite. Basically, these chips tell the location of satellite. Satellites tell the angle of each of these chips to the satellite. So the angles once received from this chip sends to the smaller chips, and the smaller chips send to the antenna, and the antenna transmits the signal. The satellite contains 4 phased arrays, 2 of which are used to transmit signals to multiple dishes, and 2 of which are used to communicate with ground stations to relay the internet traffic. This method is also used in mid-flight internet, 5G, the military data, and weather detection. So this process also explains that. The last step is transferring data. So how do we convert these signals to binary? And binary is needed for the computer to understand. This is done by using a graph that converts the wave using its amplitude and its phase to find out what point it is on a binary code, which is the binary code. The distance between the origin and the binary code becomes the amplitude. Suppose this is the binary code, which is a graph of all possible binary code, and we want to use this binary code. So we take the origin and we draw a line, and that's the amplitude. And the angle from which the 0 degree to the amplitude becomes the phase. So using the amplitude and phase that we learned earlier, we can alter the frequency and alter the wave. So each wave will mean a binary code. So by altering this, we can have like a differentiated binary code for each wave. Each of these groupings are called symbol and last 10 nanoseconds. So each binary code, which is a symbol, lasts 10 nanoseconds. Since the dish can't send and receive data at the same time, it does so at an interval or nodes. So in 1 second, it uploads at these intervals and downloads at those intervals. This whole process is an oversimplified version of the actual process and is known as 64 QAM, or quadrature amplitude modulation. And that is and then the next step is that the data sent and received is compressed to form a video. That is your known internet. And that's it. That's how it works. That is how Starlink works. I have just explained. Thank you for listening. If you have any doubts, you could contact me.